Hello, thanks for coming to this talk. I'm Ben Cerebrin. I've been working on the low-level parts of our virtualization and our hardware and our low-level software security for quite a while. And Nitro is the kind of software-hardware boundary that I enjoy working in. I've asked my kids what they think I do at work, and they think it has something to do with delivering packages or driving the vans. That would be fun, but I haven't gotten a chance to drive the van yet. I told them I help people share computers, and then they stopped listening to my practice talks, so there you go. Today we'll talk about what Nitro is and some of our more continuous innovations on Nitro that haven't been discussed in previous years of this talk. And you can see previous years of this talk on YouTube, and we've streamed them. I wanted to discuss the ways that Nitro is modular and lets us make a big variety of configurations and how they benefit the customers. They give you choices for performance and business continuity, and we have a bunch of topics on that all around the Nitro modularity. Then we'll dive deep into a further security topic that builds on our existing security module. When we started to build Nitro, we asked, how would we build a system that gives all of the compute resources to the customer, all the CPU and all the RAM and all the performance, and focuses just on running guests and no other overhead? How do we minimize access to our operators, and how do we simplify the whole system, and most importantly, make it secure? This Nitro system launched in November 2017, and we've been developing it for longer than that, and it's using our special hardware and our software that I'll go into details on. It's a whole system built out of a family of cards and components that we've designed. In the center here, we have the Nitro security chip, showing that our security is really the most important thing we do, and we started thinking about security first, and everything else follows from there. The security design motivated a lot of what we did in the ultimate design, and we have a simple security chip that we'll go into detail on that lets us build a simple model of low-level security that we then build the rest of the system on. We have a variety of Nitro cards that perform particular functions like networking, storage, and overall system control that we use for our data center operations. The hypervisor that we have is an evolution of what we think of as normal hypervisors. It doesn't do very much. It runs guests and listens to control commands, and it doesn't do anything else. So we'll go into a little bit more detail of each of these pieces. So we have a variety of Nitro cards for various purposes. The first one we have is the Nitro card for VPC, which is our virtual private cloud networking. This card looks just like a network card, except that it doesn't talk to normal physical networks. It talks to virtual networks. And otherwise, it's just a NIC. Our elastic networking adapter driver runs inside the guest, and it allows plugging in to our network card for VPC. The network driver that we have works on multiple hardware generations, and that avoids a big problem that you would have if you had a physical data center. You get a new NIC for a newer generation of Ethernet, you need a new driver. The way we've done the ENA driver, we've standardized the layout of the device structures so that the guest AMIs just work when they're moved across instance types and generations. That gives a smooth upgrade experience when you need to go from some moderate networking to some faster networking, for example. The VPC itself is our software-defined network. It does all the encapsulation and decapsulation and routing and security groups, and all of these are implemented in the card itself to keep everything locally secure. The next card we have is for EBS, Elastic Block Storage. It's our instance block storage. It appears as a normal NVMe device to the instance, but that's actually the front of the interface that we have, and the back end of it is our implementation of remote storage that's on our network. It looks like NVMe, and all the work to communicate to our remote network-based storage is done on the Nitro card itself. Because of that, it works the same for virtual instances as well as bare. It looks just the same. It's an NVMe driver. And remote storage is great for a lot of customers. It lets us do higher-level things like snapshotting and persistence. But we also have the ability to attach Nitro cards for local instance SSD storage on the machine, which is higher bandwidth, and it's good for things like transient data that needs fast access or customers that have their persistence layers. And it provides much higher performance. The history of that is for a while, local storage was nowhere near as fast as networking, and remote storage was all we needed, but NVMe standard came along and allowed SSD drives to have vastly more capacity for bandwidth and network. And so this lets customers have some choice about where their system balance needs to be. Do they need remote storage or do they need local storage? We do more work than just a plain SSD driver in our Nitro card. Normally SSDs wear out, and then the controller needs to do a bunch of work finding ready-to-use blocks that are still safe, and that causes a performance cliff to just slow down as the drive ages. We have a lot of monitoring and management in our device, in our Nitro card, to to watch for the age of the device and manage it and maybe swap out hardware or otherwise avoid performance cliffs. And here too, the virtual and metal experience are all the same. It's just NVMe. It's just local SSD NVMe instead of remote. In a few minutes, I'll talk about ways we're evolving this instant storage with even more features. So the third card we have is the Nitro card for our control plane. It provides a small API that our control plane calls to set up VMs and run them and tear them down. It controls the local resources, and it talks to the security chip and to all our other Nitro cards for managing their firmware. Our Nitro card controller is the root of trust in concert with the security chip, and they manage all of the firmware updates and just keeping the system locked down. So going into some deep depth on the Nitro security chip itself, it's a special microchip that we have, and it's controlled by the Nitro controller card, and it's at the low-level interfaces on the motherboard. It gates access to all the non-volatile storage for things like BIOS and BMC firmware, and and it makes sure that the only contents that we have on those chips is what we wanted on those chips, and we build this as our root of trust of the overall low-level system. Between the Nitro controller and the Nitro security chip, they set up policies for how the instance, metal, or vert can talk to the hardware. And they provide a nice isolation layer between the host side system, be it hypervisor or bare metal, and then our BIOS and BMC and other such things that have firmware. This has a history in the development of metal, where on a virtualized machine, the hypervisor is a nice layer of defense. It wouldn't give access to firmware to a given guest. But when we have metal guests or metal instances, we don't have any hypervisor anymore. We just have complete access for the guest to talk to the hardware. So we added our Nitro security chip to replace the virtualized layer of access control to our low-level firmware. And so it sits there and monitors all our low-level buses like I2C and SM bus and SPI, and it disallows writes to the BIOS and VMC and other firmwares. And it lets us monitor and control some of the low-level interfaces. This is a nice simplification. You know, if you buy a commercial machine, then there's all sorts of OS-based firmware update paths and things like that need to be managed and controlled. And we get rid of all of that. We use our Nitro security chip to block access and to do controlled firmware updates when we need to do them. So in the next picture, I'll show the whole system view. Here in this picture, we have a nice PCI bus on the bottom, and you know, purists in the audience would remind me that it's a point-to-point PCI Express hierarchy that emulates a bus, but I'm sure we don't have any purists here, right? And then we have the Nitro controller card on the left, card or cards I've elided in this picture, and they provide EBS storage and networking and SSD. On the right side is the motherboard of the system with the physical CPU, the Nitro security chip, and memory. And in that orange box is what an instance sees. It sees some CPUs, it sees its storage, its local storage, and its remote storage, and its networking. One of the really neat things that I like about the Nitro architecture is that it lets us plug and play lots of different pieces and make a lot of different system configurations. And we reuse the components we've built and just configure them differently for different use cases. All of the heavy lifting of being in a cloud doing a virtualization system is done not on the CPU and the memory that the user has access to, but it's on our side cards, so that all the CPU utilization is available for the guest or the metal instance to use. So I'll start talking about the various pieces we plug in and out as we build different instance types. We have an assortment of Nitro cards, generations and speeds. We have different memory contents, CPUs, and network components that we can put together. And as customers come to us with a bunch of different computing needs, from normal size, small or medium or large scale VMs, or ones that need enormous memory or enormous networking or storage or accelerators, we can compose systems that address those needs. As Adam said in his keynote, the customers keep finding that they need more and more instance variety and more beefy instances, and we're able to assemble them using the components we have. So in this picture shows one of our systems. We design really similar systems for each CPU type we offer. In this picture is an example of an Intel Generation 6 system. There's an Intel CPU in there providing M6i instances with our Nitro controller and our Nitro system all around it. Note here that the M6i, the I is a new naming feature, or naming convention we have starting in Gen 6 that means Intel. But what we can do is we can make a very similar system, but put in our Graviton 2 or now our Graviton 3 chips, and we'll provide M6G or C6G families with our Graviton chips and very similar Nitro controllers and system design overall. And then this lets customers migrate to ARM, which gives really big performance and price performance advantages. We also give choices to use another x86 vendor, AMD, and these systems look very, very similar as well. It's a Nitro controller and the surrounding components with an AMD chip plugged in instead. And now this is our newly announced M6A AMD machines. And this was one of the machines I worked on in the last year and change. I worked on the AMD Gen 5 and Gen 6 instances, and it's really neat to see all these offerings of options that we can give people. So we're not just modular in terms of CPU. We can make our memory expansion happen, and we can make much bigger memory size instances. Like the X family has 16 or 32 gigabytes of memory per vCPU, and these are all built out of Nitro systems as well. They look a little different because they have so much memory in them, but otherwise Nitro controllers and Nitro security chips around the system. And we still have other areas of modularity because this is based on PCI. We can plug in GPUs from 2 different vendors for customers who need visualization and moderate machine learning capabilities. These GPUs are just passed through to virtual machines, and we use all the same Nitro system. Similarly, we've started seeing a big abundance of training machines for Trainium and the Habana Gaudi machines for big training workloads, and there's other similar workloads that look just the same with PCI devices plugged in for FPGAs or video transcode. And again, all the system looks very similar with Nitro surrounding it, and we plug and play the components we need. For example, in many of the machine learning instances, we plug in quite a bit more networking to accommodate the data that moves through these things. So in addition to all these choices, the architecture lets us shift the system balance as the customer's needs, so we can reuse components, but make some performance changes as we need to go. For instance, we can change this Nitro controller out. We have multiple generations or types of controllers that we can plug in. And by the way, you don't have to see this picture anymore. This is the last time. We get to build up different systems with different Nitro controller selections, so we can have high network or high storage or both. And because we offloaded all this work into the Nitro controller card, the options that we do pick don't put additional burden on the host machine itself, so we still have all the CPU and memory that are on the host machine for the customers to use. So how do we apply these configurations? As Ethernet grew from many years ago to now, it went from 1 to 10 to 25 and 100 gigabits per second on a single cable, and as we grow, we've had instances that take advantage of each of these sizes. So I've listed here the first instance type that I know of that had a given speed for the machine. When we started ENA about 6 years ago with X2 and R4 instances, they supported 10 gigabit networking. And the nice thing there is once we got people onto ENA, we had a very similar model between ENA and NVMe, which have a nice generic multiple queues and NUMA awareness and a management queue. So a customer can take just a single AMI that's configured with ENA drivers and move it from instance size to instance size. So if we go from C5 to C5N, you get more networking, but you don't need to reconfigure the machine otherwise. That's a really neat way we designed this, and I think it was a pretty good design choice here. And again, because our cards are plugged in, they provide ENA for metal and verts, and there's no real difference there. Similarly, we have evolution of storage capabilities. So our remote storage called EBS grew over the years up to now 60 gigabits per second worth of storage for our biggest use case. As customers have high requirements for I/O-intensive workloads like SQL or NoSQL databases or search or analytics, they need more and more storage and more storage bandwidth, and we started providing that. One of the interesting things, the way we built the Nitro design, is that we provide a normal standard NVMe interface that allows us to iterate our design under the covers. So as we needed to go farther to the right in my diagram here, we needed to do some performance scaling solutions. We had some performance walls that we hit with the way the networking was working, and so we started using our scalable, reliable datagram networking on our implementation side to get past that 38 gigabit boundary and up to the 60. And then we can support really nice high EBS bandwidths that way. This isn't really visible to a customer other than it goes faster. It's still the same interface. It's the same drivers. It just works faster now because we've done a bunch of work on the network side. One of the neat things that we've also done with local storage is innovation where we take over more control over the SSD. So we've been asked by customers for predictable performance for database workloads and other such things that are pretty latency sensitive. You can imagine a case where the overall system needs to be architected for certain latency requirements. And as we get a system with jitter in some of the storage, then you need to start doing more engineering work to either over-provision or over-engineer to compensate for the noise sources. And customers were seeing that our traditional SSD instances were providing an amount of latency in the baseline that provided a challenge, and it had a pretty wide variety of latency variants, and that was making it difficult to engineer systems that satisfied the requirements. So some of my colleagues have a really exciting use for Nitro. They take over some of the functions that the SSD controller normally does, and we made a new product called the Nitro SSD, and that let us set a design point trade-off where we focus on lower latency and smaller latency jitter. This doesn't replace SSD options that we already have, but it adds a new set of choices for low latency. And really neat things here is that Nitro lets us iterate quickly on our side for new features as customers have asked, and we're looking forward to going into some detail in the near future on some of the features that are coming to Nitro SSD. So if we move on from one kind of latency to another, I'll talk about some of the system event latencies that happen during the life cycle of instances. So we try to make virtualization cover as many cases as we can, but there are use cases where customers just need to have the bare metal. For example, if they want their own hypervisor, or there are licensing reasons that make virtualization not the right choice. And this is a really neat solution. We just give the whole machine to a customer. But some customers have some pain points. While our virtual machines spin up in seconds because the hardware is already running the hypervisor, it's ready to go, the metal instances require more setup and bring up as they have to boot the whole thing from the customer AMI, and it takes several minutes to boot. And we've heard from many customers that the metal does what they need functionally, but these launch times add a lot of burden, and that can't be ignored. For example, we have an internal customer that has a lot of container-like workloads, and they use virtualization to provide the containers. And they might have demand spikes over their day, and they add more machines as they need them. But you might have a demand spike that comes faster than a metal spin-up can happen, and then they wouldn't be able to satisfy their container demand. So this internal partner had to work on a big management feature to keep a warm pool of machines running all the time, which is wasteful of resources, and it's a complex thing, and it's just a big pain point. So one of the things that we've done this year is we worked at multiple levels to speed things up with BIOS and hardware and the Nitro card, and we trimmed down a lot of the time spent in the metal launch. And so we've generally improved launch times by as much as 86% by doing a big cleanup. And that brings our launch time down. Occasionally, it could be potentially to under a minute in this new design. So that's pretty exciting for all these use cases that then get to simplify what they do because they can get the machines faster. Another speed up we have goes around how we manage our own firmware. So we've talked in previous years at this session about updating our system software while the system is running so we can seamlessly refresh the hypervisor and we wouldn't have too much disruption for the guest instances. It's a standard replacing the airplane engine while you're in flight. It's no big deal. Updates like this can pause your access to the networking to the storage briefly as we're loading in the new software. And we've done a major redesign of how we do our live updating and what we've done is we keep track of our state across the updates in a much cleaner way than we did before, and it manages to serialize and deserialize the state faster. And we reduce pause time significantly as well. And we should be at sub-second or significantly so on our standard instance sizes by now. So that should be a already visible thing if you're noticing your pause times going down. Now that we've talked about all these changes and these new things, I want to go back in time and talk about some things that can't change. We have a lot of customers who have built some systems years ago and they're working really well, and they're based on some of our older instances like M1, which is 15 years old at this point. And many customers are happy with the prior generation instances, and it would require a lot of work and burden to change over from the existing older prior generation instances over to new ones. And as we move to this new Nitro-based hardware, we don't want to make customers have the pain of having to do the migration. But we did launch these instances 15 years ago. We have a problem with that because the hardware is aging. We can't easily add more capacity. We can't buy more machines. Machines aren't really designed to last a decade and a half. Some of the fab lines for the chips don't exist anymore, so you can't buy more chips for replacement components. So we're out of machines. What can we do? If you take an M1 instance that was configured with the storage of the time and the networking and so on and move it to Nitro, there's a lot of things that you as the customer would need to change to make that work nicely. So what we've done is we've worked on a way to take the non-Nitro guest instances and make them run on Nitro machines. We added a layer to our Nitro system to emulate the Zen hypervisor interfaces and the device interfaces that were in the older generations. And there's a chalk talk on this tomorrow that you can go to for more detail on this. But just like our under-the-covers SRD change to storage, we didn't change the interface that was presented for storage. Here, too, we don't change the interface that we provide for Zen. It looks like the same machine, and then the upshot of that is the customer's instance gets to just keep on running, and it doesn't need to do anything more than reboot, and it's ready to go. It doesn't need an upgrade. You know, and during this process of designing this, we had a lot of discussion. Why don't we just make Xen-based hardware in newer machines? And we chose to focus on investing in the Nitro system because we had designed it for easy modularity, easy security, and we keep all our Xen-based items stable, but all our new feature work lives in Nitro. And so we want to make sure that you don't see any changes in the Xen-based prior generation instances. Meanwhile, we keep the security bar set the same for Xen and Nitro. We work hard to keep everything as locked down as we can. But the Nitro system is just more modern, and it's easier to innovate in while keeping our security bar strong. So we use the standard AWS maintenance process here. So you get a 2-week notice period that your machine will need to reboot because we need to maintain the hardware. And there's many customer controls around that where you can help choose the schedule for a given machine. Our aim is to migrate an instance just one time. It goes from the older hardware to the newer hardware, and it won't need to go back and forth. And I think this is really neat. This was a big complex problem where we have machines we can't replace and customer instances we don't want to disrupt. And this lets us use our Nitro card and leverage that that existing work to keep these compatible machines around for as long as they need to be kept. So just for a quick break, I was going to talk about my kids again. You know, I told them I delivered packages, and they didn't really believe me. So they had some gifts coming, so I put the gifts in their rooms, and then I was technically correct, which is the best kind of correct. I delivered their boxes. But one of the things I really do work on is hardware and software security and the interaction of them. And security is really an Amazon top priority, and we enable the customers to raise their security bar as well. So if we talk a little bit on the left side as how we take the Nitro chip and protect our own firmware, we make sure that we have a lot of integrity checks of the system with our Nitro security chip. It validates our software, and we have a system internally where we sign and confirm all the builds we have. Similarly, we have features to help customers do industry standard integrity on their instances. The mechanisms are different between Nitro security chip and what we're providing for customers, but the goals are aligned. And the goal is make sure your software is running the version and the code that you expect it to be running. So in the process of secure instance boot, which has it's basically an exact virtualization version of Secure Boot that's an industry standard. We have a lot of components that come together to get from the booting system at the beginning over through its OSs and into the applications and to be secured against tampering of the binaries. And whether it's in a home data center or in a cloud instance, it all looks fairly similar. For a cloud instance, we've got the AMI, which is the initial copy of the hard drive. You create an instance and it copies the AMI into the boot drive of the instance. When you start out, the AMIs aren't mutable, so it's extra security there in that this thing is not tampered with once it's been created. But the problem is that you have subsequent reboots, and those reboots come from the instance storage. And we want to be able to let the customer be sure that the OS and the binaries aren't harmed by any malware or mistake after the instance is launched. So let me take a diversion here and go into some depth on the TPM, which is part of physical and now virtual systems. This is a component of the secure boot process that we're talking about here. And since I've never found this really covered in depth to my satisfaction, so I'm trying to explain this as I wish somebody had explained it to me. So we'll go into some grotty details here. The TPM, the Trusted Platform Module, is a standardized chip that's present in almost all physical machines today. Your laptop most certainly has one. Most cloud machines have them in them. It's a small and intentionally small interface chip, and its job is to do a few small cryptographic things for the platform and to be sort of defended against from anything else that's going on. It has some identity components, which is a unique and not forgeable name for the TPM itself, and by proxy, the platform that it's in. The TPM has things like cryptographic certificates that are signed by the issuer, the vendor of the TPM, and so that's its name, and it can prove its name is this, and it's intended to be a unique name. The TPM can also hold some secrets, like storage keys for hard drives or remote volumes, and it can give them out only when certain conditions are met. And part of what it does to measure those conditions are use these PCRs, the platform configuration registers, which are used to measure the conditions of the system's boot. And we'll talk about that in some detail here. So TPMs, both 1.x and 2.0, have 24 or more platform configuration registers. And they're used to store the cryptographic hash of a log of what happened during the platform boot. So in TPM 2.0, these hashes are known to be strong SHA-256 hash. And they're like registers that can be stored to, except they can't be written directly, they can only be extended. So what a TPM register is, given a value, it takes its old value, concatenates this new extension value, and produces the hash, and that's the new value. And the purpose of that is it's an append-only log that serves as a non-spoofable record of what happened in the system. And there's usually a parallel log, which is a more complete history of it, and then the TPM takes hashes of entries in the logs and puts them into the hash and produces the next value of the PCR. The purpose being that anybody can recalculate the expected PCR value from the log and other collateral and produce a notion of whether the system is in the appropriate state or not. So I've got a little bit of a demonstration of that. So we've got PCR 0, which is one of the 24 that it has. Starts out initialized at 0, and then at some point during the boot we'll have a value we need to put into the TPM that represents for something like the bootloader. So let's say the hash of the bootloader is this ABCD, and we ask the TPM to extend to PCR 0. So it does, and it produces a hash value, which is some hex stuff, based on the old value of the PCR concatenated with the new extension. And then later on, we'll extend it with the new value. Maybe this is now the second stage of the bootloader, and it'll produce yet another PCR value. And this is some hex gobbledygook that we'll look for later on to make sure that we've repeated the same series when we need to make sure that the same history happened on a subsequent boot. The PCR values themselves initialize only at system reset, so the systems are designed that when the whole system is reset, it's back to its beginning state, so is the TPM. And so as we go, these values that are in the PCRs are deterministic, but they're one-way only. I can't rewind because of the properties of the SHA hash. So anyone who comes on later in this boot and tries to extend a value can only extend forward. They can't roll backwards. They only add to the log. And as far as any cryptographers know today, it's cryptographically infeasible to rewind a SHA-256 hash to an older value without just starting over. And to start over, we've had to reset the system, so we go back to the known state. And so remember, we can't write a PCR value, we can only extend it. And so these boot sequences that we have repeatedly extend PCR values to create an end value at the end of the boot. And so if you need to get the same value again, you have to have the same operations in the same sequence. So ideally, once you've booted once and you boot again, it does the same thing with the same PCR values. And once you've done that, you can set some rules or policies around the TPM's handling of some secrets. You can tell it, please seal this disk encryption key to PCR 0 and PCR 2 to the values that they are right now. And this disk encryption key is used to decrypt the data drive and can't be retrieved or used usefully until the PCRs are at the specified values that they were intended to be. And there's different ways the sealing can happen. Sealing actually takes an encrypted copy of it and gives it back to store somewhere outside of the TPM, but it's encrypted in a way with only a key that the TPM itself knows. And that gets around an interesting limitation of the TPM that has relatively small storage, but it can store a large number of things that it seals and unseals for you. There's 24 PCRs. BIOSes and OSes have some specifications on which PCR numbers are used for what kind of measurements, and there's all sorts of documentation to read on that. There's an interesting feature that TPM 2.0 solves that TPM 1 series didn't solve. It was called PCR brittleness, and I'll go into a little bit of detail here, but it's kind of interesting to read up on. If there's an operating system or a firmware update, now the history of the boot that you went through won't be able to produce the PCR values again, which means whatever it was you sealed with the PCR values is not recoverable anymore. And so TPM2 allows you to reseal it using certain policy mechanisms to say, here's the future PCR value I want to do because I'm about to upgrade my system. And that avoids the PCR brittleness problem. I found it pretty interesting to read up on how that solves it, and I won't go into details here, but I'll feel free to ask me. I've got a couple good references for that. So going from the physical side to our virtual machines, we've built Nitro TPM recently, and we've integrated this with how we manage our instance lifetimes. So we've got a TPM that works just the same as a TPM 2.0, and we defend the secrets in it very scrupulously because this is fundamental to the security of the system. It exposes TPM 2.0 interface exactly like a physical TPM would, and it works transparently across our lifecycle events like machine hibernation or stop-start. Once we have this TPM, this unlocks a bunch of use cases that customers have been asking for to tie to access to encrypted volumes based on passing a successful boot validation. And that gets some major features, enables a certain amount of features that people have been asking for. Linux's LUKS, Linux Unified Key Setup, and Microsoft BitLocker are both full drive encryption that depend on PCRs and the TPM for unlocking the key. And we've got, Linux has DM Verity, which is a read-only block device integrity checker that also can tie its root hash to the TPM. And then in general, the TPM allows various attestation requests to be given to it for identity and for did my boot work the right way. And so this Nitro TPM is a new feature that we're about to launch. And it's available because we've put it in the Nitro card. It works the same for virtual machines and metal. So going from TPM to the other part of the puzzle, we need something at boot that's trustworthy enough to start putting things into the TPM itself, and that forms the root of trust from the boot on to the OS. So in physical machines, there's a feature in UEFI called Secure Boot, which ensures that the bootloader itself has been signed by a known authority, and it will reject it and go look for another one if it can't find a bootloader that passed the validation. That refuses to boot in its entirety if the signature isn't good. If it is good, then it moves on, and then presumably the bootloader that was signed is something that does a good job and a known, well-trusted job of extending PCRs into TPM. So in our case, the UEFI binary itself comes from EC2 itself, and it's also immutable, so it's a bit of an extra defense in depth there. And that's the first lowest level code that runs in the instance that starts the boot process. So we've put it all together in this diagram. At the beginning of boot, the guest UEFI is put into place by EC2, and it starts extending some PCRs with measurements of the bootloader, for example, grub2. And then the bootloader measures kernels and extends more PCRs, and potentially the kernel measures some user apps. And then the disk encryption process can be tied to the PCRs for unsealing disk volume keys. And it would only do that if the PCR values are good and they represent a good non-tampered boot. And this picture is very much the same for a physical machine with a physical TPM. If you look at the down arrows, those are the failure modes. If UEFI can't find a bootloader that passes signature checks, it'll search for another bootloader and eventually give up. And then if the PCRs mismatch in the OS, then you can't get your drive encryption volume key and you can't read your data contents. And so if anything went wrong, we're in a fail stop mode where none of the secrets are exposed. It's interesting here because the AMIs that we have are immutable, so the first boot is from an AMI and it won't have changed. It's copied on guest creation. And so Secure Boot actually also helps detect accidentally using the wrong AMI if you're tying some key operations to the boot firmware itself. And any malware that's inserted into a guest drive after the reboot will be detected by Secure Boot because it will be checking the boot flow as we go. So this ultimately unlocks all these customer requirements for disk encryption and similar features. So what's next? As I mentioned, I work in interesting hardware security things, and I'm looking forward to talking about some new features in the future that I don't get to talk about today. And we'll always be announcing new accelerators and network bandwidth gains and new CPU generations. So thank you. Please ask questions and answer the survey questions, please. There's a hand back there.
Hi there, thanks for this.
Sure.
The Nitro TPM, if you're moving between actual physical Nitro servers, is that also moved to the instance, or is only specific to one actual Nitro server?
Right, so the question was, if you move from one machine to another, does Nitro TPM cryptographic payload follow the instance? And yes, we move the cryptographic payload along with the instance. So you started on one machine and then we restarted on another machine, you'll have the same cryptographic identity associated with the instance. Yes?
So I have a question. You were talking about GPUs in the Nitro system. Is it available inside Nitro enclaves?
So our GPU is available inside Nitro enclaves. The way Nitro enclaves work today is you donate a chunk of memory from your guest and say, this needs to be defended from myself essentially. Please keep it secure, and then there's a socket interface. That's the only way you can talk in and out of it. So the GPUs, I don't believe, are given to the Nitro enclaves themselves. They're still part of the main instance, and if you want to do any work, the main instance would be responsible for getting the data into them.
Okay.
Yes?
What do you see as the different use cases between the Nitro TPM and the Nitro Enclave?
So what's the difference between Nitro TPM and Nitro enclaves?
And what are the different use cases that you can see?
And the use cases. So that, hello? They both have similar purposes of let's raise the bar of security. The Nitro TPM addresses existing boot flow security implementations that exist in the physical realm as well. And so a lot of it, the Nitro TPM is taking existing technology and making it work inside instances. Enclaves is a new programming model that does it a little bit differently, where the secure boot flow is saying, I've locked down my system and made sure the whole system is secure, which, there's some gaps in just plain secure boot, where once you've booted the kernel, now it's on the kernel to make sure everything is safe and secure, and it's kernel dependent, and I don't think that the whole infrastructure is totally solid there yet. Nitro Enclaves uses Nitro itself to take this donated memory and protect it, and say, we'll help keep this out of the OS. We will take page tables and separate everything, and just have this simple socket interface between the non-protected part of the instance and the protected Nitro Enclave. And so either with a wrapper or coding directly to Nitro Enclaves, you talk to it differently, you treat it differently. It does have an attestation model where when we take off the donated memory, we will measure it and provide it an attestation, which is similar to the attestation reports part of the secure boot flow. But I think it's a simpler model. You say, this is just the thing that needs security. The guest OS doesn't need to be trusted because I've kept it out of the loop. So it's a different way to cut that design, and I think it's an interesting alternate. It's really bright in front of me, so if anybody's raising your hand, let me know. Yeah? So how is high performance networking exposed for what purpose? So how do we, the fact that we're sharing the network among multiple machines on the same host. So if you look at the instance tables where we specify how much bandwidth things have, you'll see that there's within each instance family, there's sizes from medium, large, and so on up to 48XL and things like that. And you'll see that the networking bandwidth grows as the instance size grows. And that's representing basically you're sharing one network uplink that's 100 gigabytes, for example. And if you've got half the machine, you'll have about half the networking bandwidth. And we provide limits so that you won't be harmed by a neighbor trying to exceed their bandwidth. They'll just get the bandwidth that's provisioned. Is it bandwidth or packet per second? There's a lot of complicated limiters that I'm not as conversant with, but I know that PPS and bandwidth are both involved in making sure we have fairness among the instances. Oh, can you expose sub-second metrics to see where you're being throttled in the networking? I believe we can work with you on that. I'm not the expert, but I'm happy to talk to you after and find you an expert. Yes?
With the Zen emulation, does the instance type change when that happens?
Does the instance type change when we do the Zen emulation? So if you have an M1.large, it will still be an M1.large. It will be on different hardware than it was originally, but it's still, it acts the same.
The emulation is happening.
I'm sorry?
Is there like a way to tell that you're actually having emulated Zen versus?
Do we have a way to see if there's emulated Zen or not? I don't know. One of our experts is here in the back of the room, so we can ask after the session.
Thanks.
Sure. Call out, I can't see anybody. Or else we can go to lunch. All right, thank you very much for attending.